Kia ora, year 12 and 13. Here's question 2, parts A, B and C from last year's differentiation paper. So this is 2 achieved questions and a merit question. I'm going to go reasonably slowly through these. So the first one is just a little example of a trig function with a wee bit of, tiny bit of chain rule. We have to differentiate this function. So the first thing we need to do is to rewrite it with fractional powers. Makes it much easier. So 3 times x to the power of 1/2 plus cosec of 5x. Now remember, you get a formula sheet that tells you about the derivative of cosec of x, but you have to recognize that we've got 5x, so we're going to have to chain rule on that. So dy by dx will equal 3 over 2 x to the power of negative 1/2. Right, so this differentiates to give me negative cosec x, cot x. So it's going to be minus cosec 5x cot 5x, so treating this as the inside function, but I have to multiply by the derivative of the inside function. Okay, so that's all I have to do there. I'm going to clean that up and write it like this. I think it's fine to leave it with a negative fractional power here. Okay, so there we go. That's your final answer for 2A. Let's have a look at 2B. So 2B is basically a kinematics question, a lot like you saw in level 2. We've got a particle travelling in a straight line, and the distance travelled by the particle can be modelled by this function. The only thing harder about it compared to last year is that the function is a log function. So we need to know that when we differentiate a log, we end up with 1 over the function, and then we have to chain rule, find the derivative of the inside function. So s dash of t is v of t, so it's going to be 1 over 3t squared plus 3t plus 1 times the derivative of the inside function, which gives me 6t plus 3. And we need to evaluate that at 2 seconds. So v of 2 is equal to 12 plus 3, so 15 over 3 times 4 plus 3 2s are 6 plus 1. So what does that give us? Well, we get 15 over 19, and if we get a decimal approximation for that, we get 0.789 meters per second. All right, so the next question is one of these ones where we have to look at a weird function. So these questions are such easy questions. If you've done your work, you have to have a pretty clear understanding of things like limits, continuity, differentiability, and so on. And I think last year's one was at the easy end of what we can expect for these. So if you got 3 of these 5 answers right, you got merit for that question. So that's worth 5 points. So it's well worth having a good go over of this. And as usual, Education Perfect and Delta both handle these questions really nicely. So to start with, what is the value of f at 1? Or state clearly if the value does not exist. So this is saying when x is 1, what is the value of the function? And what we're looking for here is that here's x is 1. We've got 2 things going on. We've got an open circle, which means that up until this point the function was heading along here, but then it jumps up to here. And importantly, we've got a closed-in blobby point there, and that means that f of 1 is equal to 5. If it were an open circle, we'd say that the function doesn't exist at that point. But because it's closed in, that means that that's the value of the function there. Right, next one. For what value of x does the function f of x not have a limit? So if you're in my class, you know that when I do this, I talk about Michelangelo and the ceiling of the Sistine Chapel. What we're looking for here is whether the function is heading to the same place from both directions. So for what values does it not have a limit means that I'm looking for there to be a jump or discontinuity. So let's first look at where there is a limit, even though the function is not defined. So here, there is a limit because the function is heading to the same place. At this point here, though, the function is heading down when we approach from below, and then it's heading up to 2 up there. So that's the first value where x doesn't have a limit. So at x equals -3. Right, now let's magically clean up the picture. There we go. Let's see where that happens again. Well, this one's pretty obvious, right? At x equals 1, the function's approaching staying flat at 2 here on this side, but coming from above, it's going somewhere else. So the second place, where it doesn't have a limit, is x is equal to 1. Okay, next, find all the values of x that meet the following conditions. So where is the gradient strictly positive? In other words, where have we got an increasing function? Right, so again, we'll clean it up. Well, let's look at where it isn't strictly positive. It's definitely not strictly positive through here. It's flat here. But we have got an increasing function here. So this is going to be part of my answer. And then again over here, this is going to be part of my answer. I've got to be a wee bit careful here with inequalities. So we want to have x is between but not equal to 1 and 3. And the other place where it's happening is when x is greater than 7. So for either of those two conditions, this will be a true statement. Right? So let's just have a look at why I haven't said at x equals 1. Well, that's because the gradient's not defined at x equals 1 because there's a discontinuity. Okay, so it's for x strictly greater than 1, and it's not strictly positive at x equals 3 because up there we've got a maximum and it's 0, and we're going to come to that in a second. Okay, the next one, find all the values of x that meet the following conditions. The gradient is 0 and the second derivative is negative. So we know that if the second derivative is negative at this place, that means that we've got a maximum. So there's only one of those, and it's up here. Right, the gradient is 0 and the function's concave down, if you're thinking about it in terms of concavity. So my answer here is x is equal to 3. Lastly, where is the function continuous but not differentiable? So continuity is this test that I don't lift my pen off the page. If we're looking for something that's continuous but not differentiable, what I'm looking for is any sharp pointy bit. So this stupid line that I'm drawing is totally continuous, but it's not differentiable at all of these places. So on my graph, where have I got that? Well, there's only one of those places. Here, it's continuous, but it's not differentiable. Here, it's not continuous, so it's not that point. And here, it's not continuous. Here, it's not continuous. Here, it's not continuous. And here and here. So the one that we're after, the only one, is this one here where I've got x is equal to 7. Okay, so if you got 3 out of those 5 right, that was worth 5 points or merit. Lots of different little ideas in here that are worth spending some time on. So as I said, either Education Perfect or Delta, or I think the D&D workbooks will probably have some questions like this in them. Thanks for watching.